Okay, hello, this is Dr. Muhammad, and this is another video under design of steel structures according to AISC. I'm going to talk today about member stability bracing, and the contents of today is going to be, as you can see here, first I'm going to talk about the member stability bracing, understanding and definition of it, and then I'm going to talk about the provisions that we can find regarding stability bracing in AISC 360. And then I'm going to talk about the difference between two main and traditional or conventional type of bracing called panel and point bracing. Before it was titled with nodal and relative bracing, as we are going to see. And then number 4, we are going to talk about the beam column bracing, because this is the end of the beam column series of lectures. And then the last thing is going to be the design of bracing, how we can design the bracing based on the equations. So let's go to the next and talk about the ASIC provision in the first place. So now remember that AISC is giving some provisions for stability bracing, as we are going to see in the next few slides, and it is in the appendix. So we are going to find this in the appendix as we are going to explain now. So first of all, let's remove this. If you go to the AISC 360 specification and you browse, or in the manual, okay, you can find also the specification there, and browse until that you can find appendix 6. There are several appendices there, and you are going to find this appendix titled with member stability bracing. Okay, so I'd like to read this part because it's really informative whenever that you read it from the appendix, because it would like give and clarify every type of bracing that you're going to use in general. So it starts with this appendix addresses the minimum strength and stiffness. So here we're talking about the minimum strength and stiffness, like the minimum requirement, okay, necessary to provide a braced point in a column, beam, or beam column. So we have first of all the criterion that we should take care of. It is related to strength and stiffness necessary for this bracing, and we are going to find that we have different elements that we need to provide for them this stability bracing, whether it is column, beam, or beam column. Our case, because we are, as I said, I intended to put this at the end of the beam column because it consists, or at least we can say it encompasses the requirements for stability bracing for beam and column. So this is why you are going to find that it is like going to be giving some information here related to the stability bracing of beam and column as well. So the appendix is organized as follows. You are going to find 4 different parts. The first part is related to general provisions. The second, third, and fourth, it is related to column, beam, and beam column bracing, respectively. So we're going to find that they are categorized, as you can see. So this appendix is related to stability bracing, not lateral bracing, as I'm going to give in a minute or in a second. Okay, and it deals with 3 different types of elements: column bracing, or columns, and beams and beam columns. There is an important note here already in the appendix. You can find it. I'm going to read it because it's really important. Stability requirements for lateral force resisting system are provided in Chapter C. The provisions, okay, this is for lateral force resisting systems. Lateral force resisting systems. It means that we have different types of bracing. One bracing related to that is going to resist lateral loads. We call this lateral force resisting system. This is provided in Chapter C. And the provisions in this appendix apply to bracing that is not generally included in the analysis. So this bracing, whenever that we have lateral loading coming from earthquake or wind or whatever the lateral load is, or the lateral load type, then we are going to design this bracing based on the forces that is being applied. However, the the provision in this appendix apply to bracing that is not generally included in the analysis model of the overall structure. This is commonly, but is provided to stabilize. That's the point here, and this is the key word here. It is for stability, to stabilize individual columns, beams, and beam columns. Guidance for applying these provisions to stabilize trusses is provided in commentary. So I want to highlight something that is important here, okay, which is related to what we need to differentiate between two different types of bracing. The first one is related to, let me clear everything here, Shift E. So first of all, we have two different types of bracing. One called stability bracing, which we are going to explain or going to know about it now, and the other is lateral force resisting system bracing. The first, this one, which is stability bracing, it is only provided whenever that we need to stabilize a system, okay, that is having gravitational load, if we are talking about columns, and we need to put some bracing here. So what is the design requirements based on stiffness and strength for this bracing? We are going to explain today. Okay, there is no lateral loads here is being applied, no lateral loads. However, other type of bracing, it is, we are going to find that we are having the lateral loads. Sorry, just a second. So we are having the lateral loads, and these lateral loads, they are going to be used for the design of this bracing that we are going to add. Okay, so this is what we call it, lateral bracing. Okay, let's go to the next part, and here we're going to talk about the general provisions. It's very important also for us to know about these general provisions. You can find it, as I said, the source is in AIC 360, Appendix 6. Always we're talking about 360, okay? Because we are talking about the design provisions and so on. Okay, this is the committee number. General provisions. The bracing systems shall have, as I said, we are designing for strength and stiffness. Strength and stiffness. Specified in this appendix as applicable. Where such a system braces more than one member, the strength and stiffness of the bracing shall be based on the sum of the required strengths of all members being braced. That's an important issue. If we have, for example, multiple bays like this, okay, and we want to make bracing, and we have chosen, for example, the middle one to add the stability bracing, and we have only gravity loads, there is no lateral loads. Then we need to design this bracing. There is no lateral loads here, and even in the analysis, we need not to include this bracing. So how we are going to design it? First of all, it is going to be, as we are going to see, the stiffness and strength of this bracing that we are going to provide. It should be a fraction of the gravity or the axial strength of the different frames that is going to be braced. For example, if we say that the first one is resisting, let's assume 100 ton, for example, and the second the same, and the third, and the fourth, and the fifth, then the summation of all of them, which is, if we say 500 tons, okay, this value is going to be used for the design of the bracing, okay, for the design of the bracing, whether for strength or stiffness, okay, because the required strength in the frames or in the elements that is going to be braced by our bracing is the main input parameter for us to design the stability bracing. Okay. The evaluation of the stiffness furnished. So actually, this is very important keyword here, which is the word all. Members being braced. Okay. It is based on the sum of the required strengths. Okay, strength, as I said, means that the required strengths, which is gravitational loads, for example, for talking about it. Okay, more detailed analysis. Okay, the evaluation of the stiffness furnished by the bracing shall include the effects of connections and anchoring details. That's also an important part that is included uh, in the specification. There is a note here given by the specification. More detailed analyses for bracing, strength and stiffness are presented in the commentary. And I strongly recommend for you, you can go to the commentary. You are going to find like more discussions regarding stability bracing. But because of the scope of this course, so we are going only to see how we can design the bracing and how we can understand the different types of it. That's the main goal of this course. We need to know what are the types of the stability bracing that we are having. So first we have something called a panel brace, formerly referred to as relative bracing, or relative brace. This is you are going to find in the old textbooks and other types of and older versions of the specification. They use the word relative brace rather than panel, but the new one is going to use panel brace. So in the panel brace controls the angular deformation of a segment of the braced member between braced points, that is the lateral displacement of one end of the segment relative to the other. Look at this part here. If you have, this is the element, for example, let's assume this is the column that you want to brace, and this is the bracing that you are going to use. If this column is going to move laterally like this, then the relative bracing or the panel bracing is going to prevent this movement of this end of the column relative to the other end. Okay, so that's what we call it, panel brace or relative brace. It prevents this movement, the relative movement between the two ends of the same column or the same element that being braced. On the other hand, we have another type called a point brace, formerly referred to as nodal brace. It controls the movement at the braced point without direct interaction with adjacent braced points. And I'm going to show to you what is the meaning of nodal brace in a minute. Let's go here. So this is the point brace is something like this, which is every point is going to be connected to every point here is going to be connected directly to something that is stiff enough to provide the stiffness and strength of the element that is being braced, as you can see. Okay. However, the panel is, as you can see, this is the panel of relative. We're going to find that each column, for example, is going to be braced by a certain way. This way is going to prevent the relative movement of one end relative to the other. Okay. Now let's go back. So we have here, let's assume like we have panel brace, we have point brace, and we have something, or third thing called continuous bracing system. Okay, this is continuous bracing system. Consists of bracing that is attached along the entire member length. So here we are not going to like find anything special for it because it is attached to the entire member length. Attached to the entire member length. Okay. Now let's go and dig deeper into the column bracing and let's see how we are going to understand it in terms of the two different types that we have explained, which is panel bracing and point bracing. Now let's have a look on the column bracing, this illustration. We're going to find the differences here. So we have a frame, and on the column we have loads, which is the vertical loads. And we are going to find that for any member, which is for the column, AB, for example, we're going to find that point A is braced by this strut and column, or point B is going to be, sorry, this is diagonal, is going to be braced also by this diagonal in this direction. And between them, we are going to have the strut. Okay, so this means that point A and point B, they are prevented from moving relative to one another. Okay, so this means that if we have a column that is having compression force, and we are going to provide strut and diagonals, as you can see here, then the length between A and B is going to be braced if we provide the diagonal and struts, as you can see here. Based on that, we are going to find that for a panel bracing system, for a column is attached to two locations along the column length, as you can see. So the column length, two locations, location at A and location at B. Okay, the distance between these locations is the unbraced length LBR of the column. So we call this LBR, LBR of the column, whether here or here. Okay, this is also for this column, it works well. Okay. So this is for the panel bracing. But what about for point bracing? You're going to find for point bracing that we need to attach the floor or the segment of the column to a rigid abutment that is going to provide the stiffness and the strength or the stiffness required for the system. Okay, so this is external part. So a point brace for a column controls movement only at the point it braces. That's the difference between here and the panel bracing. At this point, it is going to control this point only. At this point, going to control here, and so on and so forth. Okay. So, but however, for the relative, we are going to provide it for all the points. For example, all points, if we are going to provide it for the entire length or for the entire parts of the column, and without direct interaction. I think here direct interaction with adjacent braced points. That's the point. That we do not have direct interaction with adjacent braced points. It has nothing to do with the adjacent braced points. It is here, for example, we have like this diagonal is connecting here and here, right? Here, no. There's only this level is going to be braced. Okay, this level here, this level here, this level here. The distance between adjacent braced points is unbraced length LBR of the column. So still we are having this. This is AB here. This is CD here. Both of them, they are going to have this LBR, the braced length, the braced length. Okay. Remember, we're talking about column. Okay? We're talking about column bracing. Then let's go to another case where that we're talking about beam bracing. So in the beam bracing, we have also two different types, which is a panel bracing and a point bracing. Okay. So here we have the panel bracing. Look here to the panel bracing. So the panel bracing is going to be, as you can see here, this is the panel bracing, where these are the beams here, these are the columns that we have. This is plan. So the panel is going to resist or going to provide, okay, the lateral stability. Okay. Based on that, we're going to find LBR, the braced length, is going to be from here to here. Okay. For the case of point bracing system, we're going to find that there is a rigid support that is going to be providing the support at the middle, for example, here, and then the braced length is going to be divided here, or is going to be as it is in the case of the panel. This means that we are having a point where that all the types or all lateral movement is going to be prevented. Okay? So a point bracing system commonly exists when there is a link to an external support, such as another lateral brace, So as we are going to see here, for example. Okay, so we have rigid support and then connected. This is the point. However, for the panel, it is a system for beam often consists of system with diagonal. A panel bracing system for beam often consists of a system with diagonals, as you can see. It's diagonals. Okay. There is another part which is important for beams, and it hasn't been mentioned for columns, which we call it torsional brace. Torsional brace. And for the torsional brace, we are going to provide something in the middle that is connecting between the two beams, for example. We call this cross frame, point, cross frame. So we're going to find it, for example, if you look to it, maybe it is something like this. This type of cross frame, it prevents torsional, okay, torsional or torsion, or the torsion of the cross section of the beam. Because the beam, if we're going to look here, the beam something like this. If there is loads, even it's vertical, it may experience what we call it lateral torsional buckling, or it may experience some torsion. So we are going to provide something that is going to prevent this beam from torsion. We call it torsional brace. So the cross frame prevents twist. We call it twist, not lateral displacement. Take care, because they are totally different here. In this case, we're talking about lateral bracing. We were afraid that this beam would go like this, and this beam go like this, and this here goes like this one, and this beam goes like this. So we are going to provide some lateral stability, lateral bracing. However, here in this case, this bracing that we are putting, it is not for lateral stability. It is for torsional or twist stability. Okay, it prevents twist, not lateral displacement of the beam and the particular cross frame location at this particular location. Okay, that's very good. Now we understood what is the meaning of column bracing and beam bracing. Now let's go to the third part, which is related to beam column bracing. Beam column bracing. Beam column bracing is going to be based upon the column and the beam provisions. So we are not going to bring anything new. Everything already we have mentioned about it. So it has two different types, two different categories, panel or point, and it is going to be based on beam and column. How it is going to be based in beam and column? We're going to make summation for the requirements of the strength related to column bracing and summation of the that if we are going to design the stability bracing for beam column, for example, if we assume that this is a beam column here, okay, then we're going to bring the requirements for column stability bracing and the requirements for beam stability bracing, and we are going to sum them up, whether for strength, as we can see, as we're going to see in a minute, or for stiffness. Okay, we're going to sum them up. That's the issue here. Okay. So this is from the AIC Appendix 6, the same. You can find it in chapter or section 6.4, beam column bracing. For bracing of beam columns, the required strength and stiffness for the axial force shall be determined as specified in section 6.2. An appendix means that it is column. This is the specifications or the equations, or the section is related to column. And the required strength and stiffness for flexure shall be determined as specified in section 6.3, which means beams. I'm going to show to you the equations that is going to be used for columns and beams stability bracing, okay, in a few minutes. The values so determined shall be combined. Look here, shall be combined. Okay. So if we're going to talk about two different types of bracings, one we call it panel bracing, the other one we call it point bracing. So in the panel bracing, the strength shall be taken as, yes, the sum. of the values determined from equation 1-61, 1-65. I'm going to show to you in the next slides, okay? This is related to what? This is related to column, this is related to beam. And the required stiffness shall be taken as the sum of the values determined using equation A62, this is related to column, A66, which is related to beam. Okay, so that's the issue here. Okay, so stiffness and strength. Okay, let's go and see this equation 1-6, which is, let's for short, let's assume 6-1, 6-5. This is for strength, 6-2 and 6-6 for stiffness. Let's go here. Okay, so we have, this is 6-1 here, A61. Okay, you are going to find this under the section. It is related to column. Under panel bracing, we're going to find some readings or some something to read, and then he's talking about, or the appendix is talking about the column. And in short, is providing one equation that we call it shear strength, which is related to 6-1. And then another equation, all of this is equation actually, because it is for LRUB and SD, so it is 6-2. So all of them, they are 6-2. This is 6-2, equation 6-2. This is for shear stiffness. So we have shear stiffness, we have shear strength. So in beam column, we're going to take this equation, okay, which is from column, and we are going to sum it up with the corresponding shear strengths coming from the beam column, if we're talking about panel bracing. Okay, so we are having here shear strengths equation, which is equation 6-5, and shear stiffness equation, which is related to 6-6. Okay, shear strengths, shear stiffness for beams. Okay, I'm going to explain all these equations. Okay, so do not worry about what is inside the equations now. It doesn't matter now. Just I want you to understand the philosophy first of the appendix in determining the beam column stability bracing requirements for shear and for shear strengths and shear stiffness. Okay. Now I'm going back. Now let's go back to this controlling paragraph that we were using here. So the key that we're going to make summation for strength coming from exactly from column and beam. Column is 6-1, beam is 6-5, and the same for stiffness. We're going to have column and beam. So column is going to be 6-2 and beam is going to be 6-6. Okay, this is for panel bracing. Now let's go to the second part, which is point bracing. Point bracing. Okay, so for the point bracing, we are going to find, for the point bracing, the required strength shall be taken as the sum, the same also. We have like column B. So the column is going to be related to 6-3, and the beam is going to be related to 6-7, as I'm going to explain in a minute. And for the stiffness, same column and beam. So we're going to have also 6-4 and 6-8. 6-4, 6-8. And we're going to sum them up. That's it. This is the philosophy for beam column bracing in AIC 360, according to Appendix 6. That's the philosophy. What are these equations that I'm going to, that I have put here, 6-2, 6-6, 6-4, 6-8. What are these equations? We're going to explain them in a minute. Okay, so we have panel bracing, we have point bracing. For the panel bracing, then the equations involved are, this is for the panel bracing for column. It is equation 6-1. In the direction perpendicular to the longitudinal axis of column, the required shear strengths of the bracing system is this value. Okay, this is we call it the required shear strength perpendicular to the longitudinal axis of column. VBR equals 0.005 PR. So what is PR? Yes, exactly. It is the axial force on the column that is being raised or the frame that is being raised. Okay, the axial force, we call it the required axial strength. Okay, so PR, it is the required axial strength. PR, required axial strength of column within the panel under consideration. Take care of this word, within the panel, because maybe we are putting this bracing to resist or to make stability for this panel. If we are having more than one panel and there is no other stability bracing, then the summation would be used in this case. Okay. And the required shear stiffness of the bracing system, then the required shear stiffness. So we have shear strength, yes, we have shear stiffness. Okay. I'm going to explain what is the difference between shear strength and stiffness by an example next lecture, so do not worry about this. Okay, strength, it is related to the strength of the bracing itself, the force that is going to be developed over the cross section that we need to provide, right? However, for the shear stiffness, it means that how much lateral movement is going to be allowed by our bracing. Okay, this is what we are going to talk about it in the example. Okay, so this is delta. So here we are talking about shear stiffness. Shear, whenever we talk about stiffness, it means that what is the amount of force that we need to provide, okay, in order to provide the stiffness to control, or we can say the shear stiffness is the amount or magnitude of force that is going to displace the end point of the brace a unit displacement. Okay, this is the meaning of the shear stiffness here. And this shear stiffness is going to be 1 over, if we're talking about LRFD, 1 over phi, or 1 over phi, 2 PR over LBR. PR, you know it, wired axial strength. LBR, you know it, it is the unbraced length within the panel under consideration in millimeter. Okay, and instead of 1 over phi, we can put omega here, which is the safety factor, if we are talking about ASD. And this equation is going to be the same under, or this fraction is going to be the same. Okay, for phi here, it is 0.75 for LRFD, and safety factor 2, we're going to use it in this case. Okay, so this is related to column panel bracing equations. We have two equations here. Remember, 6-1, and these are 6-2. Okay, now let's go to the second part, which is column point bracing. So we have two equations. One equation related to, exactly, this is related to the strength, and the other equation, big equation, it is related to the stiffness. That's right. So we have strength and stiffness. Okay. And if you are going to look here, it is in the direction perpendicular to the longitudinal axis of the column. The required strength of end and intermediate point braces is going to be this amount, 0.01 PR. We know what is PR? It's required axial strength, 0.01 in this case. Okay. It is less, not less, it is larger than before. If we go here, here it is 0.005. Here it is 0.01, it is double. Okay, for point bracing, the required strength is double that of the panel bracing. And for the stiffness, in a similar fashion, we're going to find the same equation as we have used before. We know phi and omega, it is given for LRFD and ASD, and we have PR, wired axial strength in the panel, and LBR, it is going to be the unbraced length. Remember, here it is 2. sorry, 8. Before here, it was 2. Means that we are multiplying it by 4, right? So in point bracing, we multiplied, we're going to find the point bracing, we multiply the required strength by 2, so it equals 2 times the panel bracing, okay, requirement, and here we found that it equals to 4 times the panel bracing requirement. This means that we need more or stringent or more strength and stiffness requirements for the point bracing compared to the panel bracing. Okay, this is for column. Now let's provide the same 2 slides. Here we were talking about column, panel bracing, column, point bracing. Now let's do it for the beam. So we're going to have beam, panel bracing, and we're going to have 2 equations, one for exactly shear strength, which is 6-5, and one for shear stiffness, and it's going to be 6-6. Okay, so we have the equations here. This is for panel bracing. Okay, I'm going to explain each term here. Go here. This is beam for point bracing the similar way, in a similar fashion. We're going to provide a condition for strength and condition for stiffness. We have strength and stiffness, and then we have these type of different parameters. Let's go and explain about it. So the shear strength VBR equals to 0.01 MR CD over H node. So MR here is going to be the required flexure strength of the beam within the panel under consideration. Okay, using LRFD or ASD load combination. Okay, so this is MR. We are talking about moment or flexural strength. CD, it is 1. Always we take it as 1, except in the following case. If we are having a single curvature, then it is okay for the beams in this case to take CD equal to 1. But if we have double curvature, okay, if we have double curvature or point of inflection that is going to be there, and we are going to provide a bracing near to it, in this case, this CD needs to be 2. Okay, so it is equal. It equals to 2 for the brace closest to the inflection point in a beam subject to double curvature bending. So if we're going to provide a bracing here or here, for example, okay, in this case we need to look to this bracing. If it's the closest bracing to the point of inflection, then we need to use this CD equal to 2. This means that there is more requirements related to the bracing near to the inflection point rather than the other points that is going to be braced, okay, along the beam. H node, it is the distance between flange centroids. So if we are going to have, this is the beam, so we are talking about, this is H node, okay, distance between flange centroids. And for the shear stiffness, we need beta BR, which is 1 over phi times 4 MR CD over LBR H node. The same, okay, as we have mentioned, only LBR, which is the unbraced length, as we have said, within the panel under consideration. This is beta BR. Take care, we are talking about 4 here. If we go to the panel bracing for columns, just for comparison, actually they cannot be compared because we have like flexural here and CD, so it is not fair comparison between beam and column, I guess. But it is fair comparison if we are going to look to the case of column itself, in the case of beam itself, and comparison between the panel bracing and point bracing. Okay, so this is the point bracing now for the beams. And now let's go to the final part, which is design of bracing design of bracing. Okay. Okay. Now, the design of bracing, and this is actually from the textbook, you can find it in SIGWI, 4th edition. A frame can be braced to resist directly applied lateral forces or to provide stability. As I've mentioned before, you're going to find in commonly SIGWI is giving some summary of what we are explaining, but in other books like Salmon and Johnson, for example, they are providing more details about everything. So, but anyway, it's this kind of like brief summary is very effective and concise and very nice for the student, okay, and for the engineer. But sometimes for researchers, you need to find more in-depth understanding of some specific point or particular topic. So it's better to go to other references, okay? But anyway, this is very nice and good for students in general and engineers. So as we said, the latter type, which is provides stability, we call it stability bracing. Okay, was first discussed in chapter 4, which is related to compression members. The stiffness and strength requirements for stability can be added directly to the requirements for directly applied loads. The word here, added, is the key. So we're going to, whatever that you have, you can add and sum up the requirements together. That's the issue here. Okay. Now, bracing can be classified as nodal or relative. As we said, this is he uses the old terminologies. Okay, we said that nodal now is not used as nodal. It's point. Relative means panel. With nodal bracing, the lateral support is provided at discrete locations and does not depend on the support from other parts of the frame. As we have said, relative bracing is connected to both the point of bracing to both the point of bracing and to other parts of the frame. Diagonal or X bracing is an example of relative bracing. Relative bracing can also be defined as, this is the definition, that is nice definition, but it is, okay, I think that you understood what I have explained before. Here he says that if a lateral cut through the frame not only cuts the column to be braced, but also the brace itself, the bracing is relative. It is, if we go back here, you can understand this very easily from the Ellis equation. So, for example, if we're going to cut here, we're going to cut the beam and the bracing itself. We'll go to the column, the same also. We're going to cut here the column itself and the bracing. So this means that it is panel, which means relative. Okay. This is actually what is written in the book. Okay, let's go back here. Okay, the AISC requirements for stability bracing are given in Appendix 6, in general, of the specification. Stability bracing for columns and beams. Although we are considering frame stability, here, okay, it is columns, which is beam column that are being braced. We're going to see that we're going to focus, actually in the textbook he's focusing on column, relative or panel type. That's why they are like saying that we are talking about frame stability here. He wants to say that we have frames and we want stability for the frames. So we need to provide some stability bracing for the frame, which is for the column actually, or for the beam column if this element is having moment and axial force. Okay. Okay. Now let's go to the design of relative bracing. Okay. This is the design of relative bracing. Maybe this is the end part of this lecture. So bracing must be designed for both, as we said, strength and stiffness. Okay, we are talking here about design of relative bracing. This is what we are going to talk about, and this is what the example that we're going to explain next time is going to be based upon. Okay, so relative bracing. So we need to put requirement for strength, and we need to put requirement for stiffness. So for strength, we are going to use the equation in the appendix. PBR equal to 0.004 PR. Here he used 4. If you look to the appendix, this equation, okay, it has been changed. As I said, it is going to be 0.005 PR. Changed in 2016 edition. Okay, 2016. AISC 360. So in the old book, you're going to find it 0.004. The new one, they increased it to be 0.005. PBR, we know it, it's lateral shear force resistance to be provided by the brace. And PR is the vertical load to be stabilized by the brace, which we call it the required axial strength according to the appendix. In a frame, more than one column will be stabilized by a brace. Okay, so therefore PR will be the total load to be stabilized and will be the total column load acting above the brace. As we said, if we have different columns, different panels, then if we're going to use only one bracing, then we need to have all of these loads coming to the panels, okay? And this PR here is going to be the summation of all of these loads. If more than one frame is stabilized by the brace, then the columns in all of those frames must be included. Okay, this is in this equation, which is the right one here, according to the appendix 6 and 2016 version. And for the relative bracing, the required stiffness is going to be beta BR equals to 1 over phi 2PR over LB for LRFD, and the same equation here, but for omega. Okay, this is for the required stiffness, where LB, unbraced length, as we said, of the column, this will be the story height unless there are intermediate braces, and phi equals to 0.75 and omega equal to 2, as we have explained. Okay, I hope that you have understood all the equations that I have mentioned here. We're going to have an example in the next lecture, providing the importance and providing some explanation of what we have explained in today's lecture. Thank you for listening, and see you next time.